Hello everybody, this is Anirudh and this is my second presentation for my course in operating systems. As we talked about in the last video, we saw the NandToTetris software platform and going through the course materials for the first week, we learned about the basic principles of digital logic. We've worked on the first project where we've implemented logic gates in the hardware simulator. And continuing from that, we started off week 2 by learning about Boolean logic, about Boolean numbers, their operations, how they are represented in negative values. Also looked into certain parts of computer architecture. So we start off by talking about the von Neumann architecture. It's a general purpose computing model which is flexible, efficient. It has sequential nature for fetching and executing instructions. So the CPU contains the arithmetic logic unit and the control unit. It's connected to the memory to and fro. And there's the input and the output, and this is a general basic layout of a von Neumann architecture. So as I've talked, it provides this general purpose, efficient and flexible system. And the von Neumann architecture stores both its instructions and data in the same shared memory system. So this means instructions can be treated as data, they can be manipulated, which allows for the flexibility that we've been talking about till now. And it allows us to change the instructions dynamically. The CPU is responsible for executing the instructions. As we've seen in the diagram before, it controls the ALU. The arithmetic logic unit performs all of these arithmetic and logical operations, coordinates all of the fetching, decoding, and execution of instructions, takes help of some registers which store these results, intermediate results, and operands. This is a basic sketch of the ALU. It has two input lines. This F represents the function of predefined arithmetic and logical functions. And based on the F1 input, the output line is calculated. These arithmetic operations include basic ones like addition, multiplication, subtraction, division, and the logical ones include AND or XOR. The operations performed by the ALU is usually a trade-off between the hardware and the software. The ALU that we worked on in this NandToTetris platform is called the hack ALU. Operates on two 16-bit complemented values, and it outputs a 16-bit 2's complemented value. It has these 6 set 1-bit inputs, which are called control bits, and these outputs same 1-bit control bits, which we'll talk about in more detail later in the video. And this F that we've talked about, the family of functions, the total of 18 functions in the hack ALU. So this, as you've seen, these are the 6 control bits: ZX, NX, ZY, NY, F, and NO. And the output control bits ZR and NG. So we set these 6 input bits on the basis of our program. We look at our requirements and set each one according to the output that we desire. So the functions we can choose from 18 possible functions. And once we set the function and choose the control bits, we can generate the output. So we preset the X input first by using the ZX and NX control bits. Using the same procedure, we preset the Y input. And once we do that, we select between computing AND or the logical operation. Once we do that, we post the output and the result can then be generated. So this is a basically truth table where these are the outputs for different case scenarios. So that the X and Y presetting are done differently in each case scenario. And there's a selection between X plus Y, X and Y. On the basis of all of this and the function that we choose, we get a different output each time. So these are the two output control bits. So if the output is 0, then the ZR is 1, else ZR is 0. And if output is less than 0, then NG is 1 or else NG is 0. So this helps us find out if the output is 0 or less than 0 on the basis of the existence of these two control bits. And they'll come into play usually when we work with more complicated computer architecture. So this hack ALU is simple, elegant, and set 16-bit values, calculate negation of functions, compute AND or OR. And as Da Vinci said, simplicity is the utmost form of sophistication. And that's the principle that the hack ALU follows. And this has helped a lot in executing this week's project. So the project that we worked on this week is about combinational circuits. We implement all the chips that we've used last time. that means the basic logic bits. And on the basis of that foundation, we've built these combination circuits. So for finding these resources, you can just go to the NandToTetris organization website and you can download the HDR test script and compare files. Just in case you haven't already downloaded the software and extracted all of them, this is another way to do so. So starting off with the adders, this is the adder family. We have half adder, full adder, and a general 16-bit adder. 16-bit is the most famous one and the one which we worked on in this project. In general case scenarios, adder just adds two endless numbers. Half adder adds 2 bits. Full adder is a bit more powerful. It's designed to add 3 bits. This is the basic layout of a half adder. There's an XOR gate and AND gate. And sum and carry is calculated in this scenario where 2 bits are added. It's the same thing except the output for the first sum is taken as the input for the second sum. And this is the principle of the full adder. So as we've seen, the half adder calculates sum and carry. Well, sum is the least significant bit of the sum of the input and carry is the MSB. So this is a half adder. You give A and B and you get sum and carry. And this is the diagram for a full adder. As we've seen before, the sum output of two already selected inputs that's used as the input for the third sum. That's the same thing for carry 2. This is the truth table. We have 3 input lines A, B, C, and this is the sum and the output carry. Talking about the general n-bit adder, this just adds 2 n-bits. It just does not have much drawbacks like the half adder and full adder is just restricted to 2 or 3 number of bits. And coming on to the incrementer, it's really simple. It just increments the bit which you've given by the factor of n. It's usually 1 in this case. And we've also worked on building a simple ALU. It's planned and designed to function all of these operations logically. Use these simple Boolean operations. And this simple physical implementation is reduced by just using the Boolean logic gates that we have used. So this is the ALU. And this is the HDL file. This is the basic principle. We've seen the truth table before. And we built the code upon this. Upon all of these conditions, once we've said all of this, we can write in our own language how the part of the program is defined. And this is like the building block of the various chips that we're going to build coming on in the course. And it can also be done with less lines of HDL code once you optimize it. So now let's look at the programs that we've worked on. We start off with an n-bit adder. So 16-bit is the most famous one, so that's what we've done. As to 16-bit values, we use cascading full adders, and MSB is usually ignored in this scenario. This is the implementation part. You define all the inputs and outputs, and the path section of the program we write our code. So the MSB is usually ignored, and then these are the cascading full adders. Once all of this is done, you are provided with the full sum of the 2 n-bit inputs that have given. So in case you want to implement that, we use the hardware simulator provided by the NandToTetris software. We import the add16 HDL file. This is the same file as the one in the IDE. We made changes, written the code, and then we import it over here. And once we do that, we also have the script. What the script does is it loads predefined test cases. In case you don't manually input each one and then check it out, this does it for you. Once you load the test case file, the script file, which is respective to the HDL file that you just loaded, you can just run the program and view the output. So it runs all of the test cases. Just make sure the format is in binary. And then once you view the output, this is A and B, and this is the output for the sum of A. So suppose you add all zeros and ones, you get all ones. 0, 0 is still 0. You add all ones, 1, the MSB is ignored over here, as we've seen in the code. To check the validity of a program, we compare it to the compare file provided. And since no changes are made, and say that we've executed this perfectly. Going on to the half adder. This is much simpler as compared to the 16-bit adder. We just use an AND gate and an XOR gate. XOR is used for sum and for the carry. Same implementation part, we define our variables, and this is the main core of the program. We follow the same procedure. We import the HDL file, half-adder.hdl. Load the script for the same, the test script, and this is the same program as you've seen in the ID. Once we do that, these are the test cases. First, we set A as 0, B as 0, then 0, 1, 1, 0, 1, 1. So you know all the 4 basic test cases. You can run the program and view the output. So when both A and B are high, then you get a carry of 1. Else, it's usually sum is 1 and then on the both sum is 1. This is 0. You compare the output, it's the same, and this also works just as fine. Going on to the full adder, which is much more powerful, we use it to compute the sum of 3 bits. So we use 2 half adders over here and an OR for the final calculation. We do the same, follow the same procedure. We import the HDL file. All of these have been edited and worked on beforehand. Once that's done, similarly you import the test case file as well. This is the same thing, except I have 8 test cases over here because it starts with 3 bits. So 2 per 3. We choose the binary format, run the program, calculate sum carry for all of these scenarios. So 8 cases, when it's all 0, sum is 0, carry is 0, then this just goes on until we reach 1, 1, 1, then both sum and carry is both on. And in these different scenarios, we can use this principle and to calculate the sum and carry. To validate our program, we can compare it to the desired output and it's the same. This is a really simple program that I've worked on. This is the incrementer. You just add 1 to the input. That's it. So you take a section with input and then you just increment it by 1. It's not much going on over here. It's a really basic implementation of the 16-bit adder. These are the certain test cases in the script file of indicator and run the. And this you set all the inputs as first you set all zeros, then all ones, and these are random test cases. You can view the output and you can see the output is usually incremented by 1. That's all 0, it gets incremented to 1. This is a surprising case. When it's all 1, you get all 0. There's usually a 1 here, but then the MSB is ignored. So, that's where most people get confused. This is how a 16-bit incrementer works. And the final program that we worked on, the most significant one, that's the arithmetic logic unit. So we follow these principles of the HDL, ALU.HDL, where all of these case scenarios are followed, and I've written the code for this path section first to define all of the variables. 6 control bits, 2 output control bits. In paths, this is the one where we use all of the logic gates that we implemented in the first project. So we have 16-bit multiplexer, we have a NOT gate, we have an edit 16-bit adder, OR gate, AND gate. So this basically uses everything. Once that is done, we follow the same procedure. We can load the ALU chip and perform this same thing that we've done before. Script file for all the test cases. So these are different test cases where all the 6 bits are set in different values. And the function, I think, is predefined. So once that's done, you can choose the binary format and run the code. And goes through all of the test cases. There are quite a couple over here. And you can view the output. So based on these 6 input control bits, you can compare it to the desired output file, and it's the same. So we can say that this has also been a success. So this is what we worked on in the second week, combination circuits. I'm excited to see about what comes on later in this program. And I hope you enjoy the presentation. Thank you very much.